I think it's time to start, so let me start. My name is Bojun, and I'm working for LG Electronics. And here I will tell you BPF-based double-free detection tool. So before we get started, before we get into details, let me show you some result first. And here is here is a very simple double-free generating code. And here you can see that foo function is calling malloc, and bar and bot function is calling free. And on the left side, anyway, main function is calling foo and bar and bot respectively in a row, right? So this is very simply generating double free. So let's see whether the tool can detect double free correctly or not. So this is a code I showed you previously, and just I compile it, and I will run the tool, which looks like this. It will run like this. It just execute the target program, and then it will run the tool and give PID for this tool to trace. Okay, let's see whether it detects correctly or not. And here you can see that it provides backtrace information that it shows that allocation is happening at foo, and first the allocation is happening at bar, and second the allocation is happening at bots. So this is the tool I want to show you in this talk. Okay, so let me introduce myself. So I am software engineer at LG Electronics, and I have big interest in memory allocation related problems, and I do hacking for fun. And I want this talk to be interactive, so please feel free to ask a question or add any comment. In English or Korean is also okay, because I will repeat in English in here, okay? So in this talk, I will tell you the importance of double-free bug and limitations of existing tools. And I will, as this title said, I'm using some features like BPF and uproofs, so I will tell you some about these features, and then I will tell you my solution. And if we have available time, then I will show you some live demo. So let's check whether double-free is a problem or not. Here you can see the very simple code that is allocating memory, use it, and free it. And it should not be used after free, right? There is no problem. And if this program free one more time, then we said it is a double-free bug. But actually, in this scenario, it doesn't corrupt any memory, so some people might think that it is a problem, but they don't understand why this is a security issue. If we think there is another threat, then the situation is quite different. Let's say there is a memory allocation in other thread, and that could be the same address of that thread 0 is released, because it is released. So it is no problem to reuse it, right? And thread 1 will be definitely use this pointer, right? Which means because of the second free, it will use the pointer after free. So double free can generate use after free bug. One of my friends who is white hacker said that double free is rare, but if present, it is more useful than use after free for exploiting. This issue is rare, but it is still happening in real world, like TensorFlow project and LLVM project as well. You can easily search these issues, right? So, actually, many people already know that double free is very serious and important issue. So there is tons of tools that to detect double free, and I will introduce you guys in here that the tools and its limitations, and pros and cons. First one would be glibc, which is a great tool to detect double free, and it's fast and use small amount of memory, but it doesn't provide any stack backtrace information, and its detection coverage is low, which means it is bypassable. Second thing is Valgrind, which provide stack backtrace information, and its detection coverage is high, but the speed is very low, and it uses a lot of memory. And there is address sanitizer, which is also provides stack backtrace information, and detection coverage is high, but it is faster than Valgrind, but it is still slow and use a lot of memory. Actually, this kind of big overhead is sometimes not acceptable for such like embedded Linux. And this kind of overhead actually deepens Heisenbug. It's quite familiar with you guys, I guess, yeah? Why? Because why this kind of issue is happening? Why? The reason is that the debugging tool changed timing and it changed memory footprint. That's the reason why Heisenbug is deepened. That deepens Heisenbug. So I will introduce my solution, but before that I will tell you some background knowledge, background features about BPF and uproof. First one is BPF, Berkeley Packet Filter. It is virtual machine, which is running inside Linux kernel. Since it is a virtual machine, it is obvious that it will run various logics, which means this feature makes kernel to be programmable. And there is one facility that is BPF map, so that various logics could save some data on BPF map. I mean, read and write some data on that map. Next one is uproof. This is user function hooking feature. Let's say there is a code like this. There's a function named foo is calling bar, and let's say we attach uproof to the instance of the bar function, and then that uproof take the control and it could do something, and then its control is going back to bar function. So with this feature, you can hook user function. So now I can tell you the solution. Which is very simple. On allocation, here I mean allocation means the target program is allocating memory. So it is calling malloc, calloc kind of things. At that time, it hooks that memory allocator functions and save backtrace information. And then it save the address of allocated memory and set counter as 1. And on deallocation, it will hook free function and save backtrace information. And then it decreases the counter by 1. And it reports over free if the counter is -1. And this is an architecture of double free tool. Statically, double free tool consists of 2 parts. One is user level code, and the other is BPF bytecode. On runtime, the BPF bytecode is loaded to BPF virtual machine and attach uproof to the target process's malloc free kind of memory allocator functions. And if the target program executes that functions, that will trigger the BPF bytecode, and that BPF bytecode runs the algorithm I told you previously, which will save backtrace information on BPF map and set counter and decrease the counter on, which is all happening between BPF bytecode and BPF map. And if that BPF bytecode found double free, then it will trigger that it found it, and this user level process, that code will read that backtrace information which is saved on BPF map and report it to user. So let's check whether the limitations I told you is solved or not. First of all, stack backtrace information is provided, which is I already showed you at first. Excuse me. And its detection coverage is high, and its speed and memory usage is, overhead is low. Actually, that's because Valgrind and address sanitizer detect double free, and it could detect a lot of memory-related problems. So they are doing much more, so they have big overhead. But this tool just detects double free, so that's why its overhead is very low. And with this low overhead, which will minimal impact on Heisenbug. And that's because there's one more reason why. Because I said previously that if memory footprint is changed, and that will affect a lot, but this tool saves data on BPF map. That's the reason why it will minimal impact on Heisenbug. So now I will.
So you wanna hook
Can you speak a little bit louder so I cannot hear?
Okay, so why should we switch to kernel mode when you want a full user space function?
Actually, we don't. The question is that why uproof should switch to kernel mode. Because BPF is located on kernel level, so that's the reason why the facility itself is already located on kernel, so that's why we have to switch to kernel mode. Yeah, because I'm using, BPF, so that's the reason. Actually, I understand what you're talking, that is, okay, later let's talk a little bit more. Okay.
Can you show your two-thread example? Can you show your two-thread example?
Two-thread example? Yes?
In case of your solution algorithm, with that algorithm, this case cannot be detected because you assume the same address is assigned in the thread 1. So the counter is increased at that time. But in the left thread, left feed, it counter is decreased to 0, not -1. So this example cannot be detected with your algorithm.
So he's saying that in this case, my tool, the algorithm, cannot detect double free because, first of all, it is correct, right? Okay, because it is correct because here you can see that allocation is happening and free, and just it is hooking and do the algorithm I said, so it is normally allocating and free. So in this case, the tool cannot detect it as double free. It is correct, yeah. But so you're right that the tool cannot detect potential double free bug, but it detects actual double free issue. This tool, that's the point. Yeah, you're right.
So this means the user-free violation will be occurred in X runtime.
Yes, right. My tool algorithm, as you can understand easily, that is not for potential double free, but for actual double free issues.
For this case, how about locking the thread ID also?
That could be great, but I didn't actually go that far, so yeah. Maybe I can think about to detecting potential double free. Yeah. Thank you. Thank you for your idea. So, can you move on, or any comment, or okay, let's move on. So here I show you some example, sample code and show you live demo. And first example is actually I showed you at the beginning. So let's move on to the second example, which is I told you that glibc is bypassable. So I will show you that bypassable example that glibc cannot detect double free, and this tool can detect double free. So here is the code I want to show you, and it is same foo bar bot function, and I add these two lines of code. One is for bypassing I will not explain the details of why it is bypassing gdbc's detection. And the second one is just show you that it doesn't abort it, and it is executed normally. So let's compile. Here is the code. And let's compile this code. And let's run it. gdbc is automatically used in default mode, so it should be detected, but I mean, double-free, gdbc can detect double-free, but it is bypassed, so it cannot detect it. And let's run my tool. So here, the same, and it's run the sample code and pass the PID to trace, and let's see what will happen. Let's try it again. And here you can see that it is finding normally that foo bar but is called, right? Okay, next thing is about C++ smart pointer. Some people think that if we use C++ smart pointer, there will be no double-free or there will be no memory leak, but that is not true. So let me show you some C++ smart pointer example, and I will compare that the BPF double-free tool and address sanitizer, which means address sanitizer is obvious that it will detect it, and the tool also detect the same issue. So the code looks like this. So I guess some people may be unfamiliar with C++, but here you can see that here you can easily see that there is no malloc, no free, or no new, or no delete. So here you can see that making unique pointer in here, and it is released. So actually, dp is raw pointer, and it is passing to bar and bot function, and bar and bot function is making smart pointer, so it will call the destructor at the end of this function, and it will call free function. So the free function will be called at bar first and on bars second, right? So let me show you the live demo. So here is the code I showed you before. So foo bar but same, right? Let's compile it. And let me show you the address sanitizer case first. So here you can see that on compile time, first of all, it is showing that it is detecting double-free correctly. And here you can see that if you want to use address sanitizer, you can add this fsanitize address on compile time, and then you can just run that binary, then it is using address sanitizer. And here you can see that it is detecting double-free, and it is saying that double-free is happening on here, here means bar function, which means second free is detected, right? And it is showing that it is deallocated at first time is here, which is bar. So the order is different from my tool. So bar function, and it is allocated on foo. As I said, the order is reversed with my tool. So here is the address sanitizer case, and I will run the tool again. I will run this sample code, and I will run the tool with attaching to this sample. So let's run it. And you can easily find that it is detecting double free correctly. And I didn't develop demangling function yet, so actually some may know that it is new. And here you can see that make unique and foo function. So it is allocation. It is providing correct allocation. And first, the allocation is happening at bar here. And second, the allocation is happening at bars. So I'm thinking about to detecting double free bug on kernel, and I should implement demangling for C++. Okay, thank you.